Hello, ladies and gentlemen, and welcome to the OEM Session by VDMA. My name is Miriam Solera, and I'm responsible for wireless technologies in the VDMA, the Mechanical Engineering Industry Association, and I'm very happy to be able to present you today 3 top speakers which are driving innovation in very different applications fields, which are autonomous navigation for mobiles, robots, and transport systems, mobile peer-to-peer communication, and efficient and central drone operation management. Please be aware that you will be able to access all the videos and presentations on demand at the website at CMM, and that you please feel free to write your questions at the Slido window, which is on your screen. So we're moving on with our first guest. I'm very glad to welcome here Professor Jens Lambrecht, co-founder and managing director at Gestalt Robotics GmbH. Hello and welcome to the CMM.
Hello, Dr. Solera. Thanks for the nice introduction.
Let me just talk a few words about you and Gestalt Robotics.
Sure.
Gestalt Robotics is a scale-up working at the interface of industrial automation and artificial intelligence, and it's pioneer industry-ready closed-loop control via 5G, 4G, and Edge. And Professor Lambrecht is junior professor at TU Berlin, leading the chair for industry-grade networks and clouds, and co-founder and managing director at Gestalt Robotics. And you are going to talk us about semantic mapping and navigation, and intelligent autonomous mobility through artificial intelligence, and in the context of edge computing and 5G. So please, we are looking forward to hear you. Go ahead. Thank you.
Okay, thank you very much for the introduction. Hello and welcome to my talk at CMM 2020. I've been participating last year. It was a great event in Hanover, and I hope to be there again next year at 2021. So this talk is introducing crucial computer vision and AI technologies for intelligent factories of the future, made possible with 5G and Edge AI. In specific, I will talk about closed-loop control via the edge and novel technologies in regards to mapping and navigation for mobile robots. So, Gestalt Robotics is a leading service and technology provider at the interface of industrial automation and AI technology. Our company's overall technology is primarily based on 3 pillars. First, technical modularity, coming with a broad basis of industry-grade control and computer vision software functions that are typically provided as microservices in order to provide individual automation solutions with minimum effort. Second, we rely on networking and virtualization, utilizing cloud and edge computing for scaling applications, as well as usage of modern 4G, 5G radio networks in production and logistic environments. And the last of our pillars is artificial intelligence, as already mentioned. We are exploiting mostly machine learning services and technologies in order to create added value in terms of efficiency and flexibility of automation systems. With the help of these 3 technological pillars, we are active in 4 overall application fields. There's first AI-empowered computer vision, there's intelligent robotics, there are adaptive worker assistance systems, and there's autonomous mobility for mobile robots and transport systems. And so today's talk is in the field of autonomous mobility combined with AI-empowered computer vision. But before we enter this specific field, I would like to introduce a paradigm of cloud robotics, as this is crucial for taking the intelligence of robots to a completely new level. We have been considering the evolution of locally connected robots to first cloud-connected robots in the era of Industry 4.0. Whereas the cloud has been used in this time mostly as data source and data sink, nowadays we are facing cloud and edge computing, taking flexible AI software services to the machines on the shop floor, providing platforms that enable new business models and the provision channels for industrial software. So this is a completely new situation that we are currently facing. Towards edge and cloud computing. From our point of view, offloading software functions to cloud and low latency connected edge devices provides many benefits all along the life cycle of industrial automation software. First of all, commissioning and deploying of software are much more easy. Software updates can be deployed on the fly and must not be transferred to every machine controller on the shop floor. In terms of operation, we have the opportunity to set up intelligent software systems that share information and scale seamlessly. In addition, we are no longer restricted to limited computing resources of local machine controllers. And moreover, distributed automation systems provide the opportunity to create open ecosystems preventing vendor logins. In mobile robotics, that means, for example, controlling mixed fleets through a unified software basis and standardized interfaces. We can also reach longer operating times of mobile robots through offloading extensive computation, as well as minimizing the cost of the onboard computing hardware. And again, offloading software services to cloud and edge platforms may lead to novel business models and ecosystems that are currently about to evolve and will take a firm role in the flexible production environments of the future. So let us now jump into some pioneering work and providing autonomous navigation, including closed-loop control as a service for mobile robots. So this specific project I will talk about is based on one of the first 4G campus networks here in Germany, as well as edge computing. So this pilot project was yet transformed towards an industry-grade application. What started for us about 2 years ago as a proof of concept for even offloading real-time critical software functions for mobile robots to the edge finally developed into a proven and certified next-level industrial solution. During the last years, we developed a microservice-based modular navigation stack that relies on an open middleware solution in order to connect cloud and edge seamlessly with mobile robots and transport systems in the field. This scenario involves the offloading of the whole navigation stack, even real-time functions to the edge, but still relies on particular functions for person safety, for example, that remain on board. The overall solution bears an extension towards auto navigation, connects other machines and ERP systems, and is meanwhile CE certified. Let's have a look on this application in practice in a little video. You see a totally edge-navigated mobile robot transport system at the Osram plant in München. So this transport system is transporting coils between 2 stations, and the environment is quite challenging for fully autonomous navigation, as the floors that you can see there are narrow and humans are moving around. The communication also covers control of end-to-end functions regarding doors and stations, as well as the initialization of the workflows in regards of fire emergencies. So I may skip this video here and jump to another one, because we are even extending this approach towards edge-based navigation as a service, towards outdoor navigation with an extended sensor stack. And of course, also the navigation stack is extended, because outdoor navigation is a lot more challenging than purely indoor navigation. And we are currently still working on this software stack. And the overall objective is to provide a seamless navigation stack for indoor and outdoor navigation on factory premises. I also may skip this video here. So these videos are available on YouTube. You may watch them later in full length. On top of the navigation, we are considering further edge-enabled AI functions that let us provide a deeper visual understanding of the environments. So in this video, you see the result of different deep learning-based software services on the edge that run in real time, processing a camera stream from the mobile robot. On the left-hand side, you see semantic segmentation, giving forward-looking scene understanding in terms of obstacle and path. On the right-hand side, you see asset detection trained on a specific data set for machines and goods of production. These machine learning-based functions can be used in accordance with GDPR, and the processing on the edge can be extended using depth images, enabling further localization of assets. We see that in another video. If combined with environmental maps that the robots are using for navigation, we create semantic maps of the environment that are a key enabler for a series of value-added functions. This video shows the recent piloting projects we did together with T-Systems at the CCI in Aachen. And you already see different use cases here, for example, locating assets, and on the upper right-hand side, you see the semantic map that we are creating based on 2D laser scanner data of the robot and localized assets that are here drawn by icons on the map. So semantic maps leads us finally towards the creation of up-to-date digital layout twins of factories and logistic environments. And that is a totally fascinating novel field for applications. As depicted on this slide again, we add information on localized objects on the environmental maps that the robots are creating and using for autonomous navigation. In the video, we have seen first application examples towards visual asset tracking and lost and found applications that are triggered by ERP systems, for example. Now, finally, let's dig a little bit deeper into novel services we can provide based on these technologies. First of all, we can make the navigation of the robots more intelligent. That means that due to environmental understanding, we can improve the performance and the safety of the navigation through the incorporation of semantic information. Second, we are able to map environments in 2D and 3D and add semantic information, which provides a deeper understanding, enabling, for example, visual stock-taking applications or providing a general worker assistance. Finally, we are also able to collect and analyze spatial temporal information up to creating these up-to-date live digital twins of factory and logistic environments. This approach can be even extended towards static cameras, as shown here on the right-hand side, showing a digital twin for traffic guidance on an exhibition grounds that we made as a concept study for a potential customer. So these digital twins may support both in the future, automated and human decision-making, and opens up more applications that are yet to come. We at Gestalt Robotics are looking forward to shape the future of factories along with our partners and customers. So let me close with a brief reference towards our company services, highlighting the development of tailored solutions and approaching new areas in a typically co-creation mode with our partners. So thanks for listening our talk. I hope we could raise an interest for edge and 5G enabled AI technologies and autonomous navigation technologies for mobile robots and transport systems. And now I'm looking forward to answer a couple of questions. Thank you.
Thank you very much. Professor Jens Lambrecht. It was a very impressive presentation and the videos were quite impressive. I have some question for you here. Please, dear visitors, make your questions by using the window slide, slider window, which is on your screen. So we have here one question, and it is, what about the scaling of the presented use cases and the respective role of 5G in this scenario?
That's a good question, because we started with 4G campus networks, and we started with purely streaming out navigation data from laser scanners, because standard navigation in indoor environments mostly relies on 2D laser scanner data. You can very robustly navigate with this kind of data, and if you stream it out towards the edge, you just have a maximum, let's say, 100 kilobytes per second data traffic that you have for uploading. But if you, so this use case could even scale in 4G scenarios. But if you're considering the additional sensor in data that we are, for example, having in the outdoor navigation case, where we are considering stereo cameras, or if you're considering this semantic mapping cases, or you want to do, for example, inventory assessment with a robot, and you put a camera on it, and you want to know how many goods are in a specific room, for example, that means that you have to stream out the camera data and maybe also depth images. So this could be easily, let's say, more than 1 megabyte per second. And for these use cases, if you want to scale it, if you do not want to have just one robot in the overall system that you have, 5G is heavily recommended, and 5G even makes the scaling of these kind of use cases possible, because with 5G, with 4G, the bandwidth is definitely not enough there.
Thank you very much for your answer. I don't see any more questions, so I just thank you very much for being here at the CMM 2020. Professor Jens Lambrecht, co-founder and managing director at Gestalt Robotics, and I'm looking forward to see you again next year. Bye bye, and thank you again.
Thanks for having me. See you all next year. Bye bye.
Bye. So we're moving on, dear ladies and gentlemen, and please remember all the videos and presentations are available on demand, so if you missed it, please, you can always have access at it at the CMM website. So I'm very glad we're just jumping to another area. It is peer-to-peer communication in the factory. And to this topic we're having here in studio, our next guest, I'm very happy. This is Christian Sauer. Christian Sauer from SEW Eurodrive Research Engineer. Welcome to the CMM. Christian Sauer is working on his PhD close to finishing, and he is focusing on communications for multi-robot system in industrial environments and new communication technologies, visible light communication and radar. And to this topic, he's going to give us more information. Please go ahead. Thank you very much.
Thank you very much for the introduction. And welcome to my presentation about mobile peer-to-peer communication in the industrial environment. As Ms. Solera told, I am currently in the process of making my PhD and researching the communication of multi-robot systems in the factory environment. And the peer-to-peer communication is one of the foundations of this communication, of the communication possibilities in the factory of the future. So, regarding the factory of the future, we actually heard quite a lot in the past day and also today. So here are some of the typical trends that were mentioned. For example, virtual reality, cyber-physical production systems. And today I want to focus on the smart logistics. So a logistical system within the factory in the future will not only control the material flow, but actually the production process by controlling the path that certain tools or certain materials take through the factory. For this task, many of the intralogistics will be automated. Here we have an example for 3 of these automated guided vehicles or mobile robots within the factory. The tasks of these mobile robots can be very heterogeneous. For example, I have a classical AGV, which mostly transports goods, materials, and maybe tools through the factory. We have a mobile logistical assistant, which assists the worker in the assembly of pieces on a production line, and maybe even mobile robotic arms, which can complete simple manipulative tasks to the workpiece. Now, if I'm looking at all of this, at the robotic fleet, at cloud computing and big data analytics, there's one enabling factor for all of these trends in the factory of the future, and that is the communication. So let's look at the communication in the past years, today, and in the coming years for the factory environment. 10 to 15 years ago, it started with some of the standard communication technologies, like, for example, Wi-Fi, Bluetooth, and Zigbee, depending on the application. And we were mostly present in the 2.4 gigahertz band and below. Currently, or a few years ago, private cell technology was introduced to the factory, and the carrier frequencies of, for example, Wi-Fi expanded. So now we have, again, the 2.4 gigahertz and below, but maybe also 5 gigahertz communication in order to have a more widely spread spectrum communication. Now today, there are even newer Wi-Fi standards. We have millimeter wave communication in the 60 gigahertz band and also 5G communication. And 5G has a very similar spectrum spread as Wi-Fi by now. So we have frequency bands from below 2.4 gigahertz, but also up to 60 gigahertz, so in the millimeter wave spectrum. And in the future, more fascinating communication technologies will be added to the factory floor. We have, for example, radar communication, again, 60 gigahertz, so in the millimeter wave frequency, and, for example, visible light communication here, we are in the terahertz spectrum. Now, if I look at this, I see the trend that as time moves on, the carrier frequency in my factory, but also in other applications, rises and rises. This is simply due to the fact that with a higher carrier frequency, I can encode more information, which I can use for more reliability or more throughput. But this also has a disadvantage, and that is the resistance to signal attenuating obstacles, or broadly speaking, the distance that I can communicate over. So in the future, it might be very interesting to look at the coverage problem within the factory. And for this, I want to talk about peer-to-peer communication today. If I'm talking about peer-to-peer communication, I'm referring to any kind of communication where the communicated data is transferred from one mobile client to another mobile client without passing network infrastructure like a base station or an access point. Within this talk, I also include communication technologies where, for example, the management of the frequency bands is still done through an access point. So maybe I have a controlled data flow to an access point or to infrastructure, but I have no data flow to this participant in the communication. Also interesting for the industrial application are wireless sensor networks. These can also profit from the technologies I'm going to introduce or from the results. The mobile peer-to-peer communication can generally be divided into two different types of communication networks. I have the relatively dense mobile ad hoc networks, or MANETs, and the very sparse delay-tolerant networks. In a MANET, all of my clients are always connected to each other, so I can always find a multi-hop route from client A to client B. In delay-tolerant networks, in contrast, this is not the case. So there are times where single clients or client groups are not connected to my network, but I can still store messages and then drive to another position and forward this message to the destination, for example. An interesting development regarding MANETs in the last years are the specialized mobile ad hoc networks. A very big topic currently are VANETs, so vehicular mobile ad hoc networks, and also flying ad hoc networks for UAVs, for example. Within the factory, we introduced both kinds of technologies, so MANETs and DTNs, and I'm going to mention the advantages of these technologies, these are twofold. On the first side, we have performance advantages. So in certain use cases, my peer-to-peer communication actually outperforms centralized communication or infrastructure communication. It may decrease the latency of a communication and also increase the reliability of my communication. On the other side, I have a coverage advantage due to my communication technology. If I have a communication technology like Wi-Fi or 5G, this might just add more flexibility or redundancy and therefore reliability to my communication. But if I have very high frequency communication, so millimeter wave, radar and visible light communication, for example, this is actually a necessity in order to have a sufficient coverage within the factory of the future, simply because I can't place enough base stations and access points with radar communication in the factory in order to have full coverage. So now I'm going to present some of the research results I had within the last 2 to 3 years regarding the benefits of this communication technology, so peer-to-peer communication, and also regarding the research contributions that we achieved during this time. Let's first look at a very specific use case of 2 mobile robots cooperatively transporting a bulky object. In this use case, I have normally one leader robot and one follower robot. The leader robot just completes its path through the factory as before, and the follower robot receives the position and speed of my leader robot and adjusts its own position and speed in order to hold the position as precise as possible. And generally, the goal is to reduce the force that is induced into the transported object. So, as the arrow symbolizes, I can, of course, transmit this data directly between from my leader to my follower, or I can transmit it indirectly through an access point or base station. Depends on the kind of communication technology I'm actually using. But this adds latency to my communication and it adds unreliability. Simply from the fact that I have to traverse the air interface twice. I have to traverse it from the leader robot to the access point and from the access point to my follower robot. But even more importantly, the 2 air interfaces between the 2 robots and between the robot and the access point are barely comparable. Between my robot and access point, I have a relatively long distance, so maybe 15 or 30 meters. I have many signal attenuating, maybe reflecting or refracting obstacles, and I have relative movement. So the distance and the presence of obstacles actually changes. And I also might have handovers between access points. So maybe the robot group changes from the coverage area of one access point to the coverage area of another access point. In contrast, for my peer-to-peer communication, I have a very short distance, maybe 1.5 or 2 meters. I have no obstacles on my path, and I have very little relative movement, simply because the control loop within the follower robot is optimized to reduce this relative movement. So we tested this with 2 different communication technologies, which use 2 different network topologies. We had Wi-Fi in the normal infrastructure mode, so with an access point in between, and visible light communication, which was not able to be tested in an infrastructure mode. The usage of visible light communication was actually enabled by implementing the peer-to-peer communication. If I'm comparing these 2 communication technologies, I see that normally the latency in my Wi-Fi communication is quite a bit lower than in my visible light communication. So in about 85 to 90% of all my messages, the latency Wi-Fi should actually outperform visible light communication. But in this application, we see in the cumulative distribution function of my latency a very long tail on the Wi-Fi communication, and that are peaks. Peaks within the communication caused by changes within the signal propagation path. And these peaks, for example, every peak over 50 milliseconds, drastically decreases the performance and the results that my control loop can actually achieve. So if I have high peaks and high variance within my communication latency, my control loop suffers as a result of this control loop. In this example, the number of latency peaks above 50 milliseconds is actually reduced by about 99% when switching from the infrastructure channel to the peer-to-peer channel. So some of this 99% might be caused by the other communication technology, but most is caused by using the much friendlier channel in regards to signal propagation. And this overall reduced the maximum control error we had. It reduced the variance within the control error, and therefore the forces introduced into the transported object. So that was the first advantage, and as I mentioned, the other advantage is coverage. Normally, if I plan a factory nowadays, I have wireless communication in mind. So I don't just build a factory and place some access point in the hopes that everything will work. Quite the contrast, I make a lot of effort in order to plan my factory, simulate the signal propagation, and have the optimum number of access point or base stations within the factory in order to guarantee complete coverage. This is already a lot of work. And we can still not really guarantee coverage because, firstly, the factory might change. We might move machines, but also the mobile robots are moving, maybe metal boxes are moving, and I might have faults in my infrastructure. For example, a faulty firmware update on an access point. So overall, I can't guarantee the complete coverage within the factory. So I want to now compare the direct infrastructure communication within a factory to a communication solution that includes a side link-like communication. So in this communication technology, I can not only communicate directly between my access point and my mobile client, but also from the first mobile client that is directly connected to the access point to one second mobile client. So I have just one peer-to-peer link in this case. And if I compare the coverage, my direct coverage per access point is only 3,000 to 5,000 square meters per access point within the factory, while my indirect coverage goes up to 4,000 to 7,500 square meters. And if I have my pre-planned factory with all the access points and I now gain additional coverage, I can actually close holes within my coverage that are caused, for example, by movement and changes within the factory, but also maybe cover parts of the area of another access point. So that are the advantages, but there's another advantage generated by having this side link communication. And that is, if both of my mobile robots are within range of my access point, I now have multiple routes between the mobile devices. I can either directly communicate to it or indirectly communicate to it. And if I exploit this communication by introducing a multi-route redundancy within my routing technology, I can actually increase the route lifetime, so the time a communication can be done between two mobile clients by up to 100% if I include only one additional link. Okay, so much for the advantages of a peer-to-peer communication. Now for our contributions to this research field. Generally, if we want to include this peer-to-peer communication to the mobile device of the future, then it will not simply have only the peer-to-peer communication or only infrastructure communication. So it is most likely that I have multiple communication technologies and multiple different network topologies just to gain redundancy within my communication, so that if one communication solution has a fault or cannot offer the quality of service requirements that I have, another communication solutions might. Now, looking back at these advantages, I want to mention that not all of these advantages are always relevant or present. In the last presentation, we heard a little bit about cloud robotics. And if I have cloud robotics, I can, for example, solve this cooperative transport tasks also with a cloud robotics solution. In this case, the speed and position of my leader robot is never transmitted to the follower robot, but the control task is actually completed within the cloud. So the performance advantage are negligible if I have not much autonomy on my robot. But as soon as I have some autonomy on the robot and can directly interpret the values or measurements from other robots on my mobile platform, then I gain the performance advantage of peer-to-peer communication. However, the coverage advantage is still relevant. Also, if I use cloud robotics, maybe it offers even the necessary redundancy for cloud robotics. Now, there was the question of how to integrate a complex, heterogeneous, and multimodal communication solution to such a mobile client. That's not that easy because a mobile client generally has multiple running applications, maybe one for navigation, one for control, one for the safety. We have multiple different communication technologies. In this example, visible light communication, Wi-Fi, and 5G. And every of this communication technology also has a different wireless channel which changes over time. My applications might also communicate to different destinations. So some might always communicate with the cloud, some might need to communicate to other mobile clients. We solved this routing problem by introducing a software or hardware router which can fulfill some of the necessary tasks. For example, an automatic traffic classification. So it classifies the traffic regarding the necessary quality of service parameters, the destination, and so on. At the same time, we measure the channel quality for all of my wireless communication solutions. The router obviously does the routing and also might have additional capabilities like store and forward if a delay-tolerant network is introduced. So that's the contribution to the integration of peer-to-peer communication to the mobile client. Now for a very different challenge. And that is, if I have such a novel or new communication technology, it's often a challenge to just integrate it into a factory because the stakeholders in the factory are very interested in having a reliable communication and guaranteeing that everything works and the communication does not affect the performance of the robots. So I actually want to simulate this communication and especially the impact that this communication has on the performance of my mobile clients before integrating it to my factory environment. Now, before, network simulation was often done using a very linear model. I had a very simple environment model, a mobility model that created the positions for my clients, then a wireless transmission model in which I could, in a very simplistic way, include my my environment or the type of environment I'm in, and then the network model for the used communication technology, for example, Wi-Fi or 5G or LTE. And then I could evaluate the network performance. So I had, for example, the throughput or latency within my factory. And when designing a network for a factory, this was also the requirements that must be set because it was the only thing that I could check. So I could, for example, have a requirement that everywhere within the factory I want to have a certain remaining signal strength. But that actually does not really tell me anything about the performance of my mobile client. So we wanted to solve two problems when simulating this factory of the future. The first is we want to simulate the signal propagation properties of the complex industrial environment. And we want to simulate the interaction between the behavior of my mobile client and the network status or maybe the messages that are transmitted within the network. So we introduced, for example, movement paths into the environment model and the presence of signal attenuating obstacles in order to use them for the further modeling. We proposed a new mobility model for the mobile clients, the task-oriented graph mobility model, which is much more precise in modeling the AGV behavior within the factory. And we recommend the attenuation factor model for the signal propagation within the factory. And we now have a feedback loop from my network model in terms of maybe network state or messages within the network to a behavioral model that is attached to my mobility model. And now I can use the mobility model to, for example, decide how many destinations did my mobile robots reach within a certain time frame. And I can map the performance of my robots in terms of tasks, completed tasks per hour, as a function to my used networking technology. This network architecture and the model architecture and the used models are very scalable, so we can simulate hundreds of thousands of robots within a factory, and also very flexible because we still have the border between the different models. So I can just change my network model, for example, for a 5G or a LTE model if one is actually available for the factory environment. Okay, now to conclude this talk, generally, we could experimentally show that in the factory environment, we have very interesting advantages by including a peer-to-peer link. And we are still doing research in regards to the simulation and in regards to the inclusion of this technology to the factory of the future. And that will also be some steps for the future. So we are interested in simulating other types of factory environments, for example, than the ones we currently have available to us. Okay, thank you very much. And I'm open for questions now.
Thank you very much, Christian Sauer, research engineer at SAP Eurodrive. It was a very interesting and comprehensive presentation. Thanks for it.
Thank you for
Ladies and gentlemen, if you have any question, please feel free to write and send them via Slido. I have one question, Mr. Sauer, and this is, what communications technologies can be simulated for the proposed model architectures that you showed?
Okay, for the model architecture, we have currently implemented the visible light communication and the Wi-Fi communication in the IEEE 802.11 BGN standard. And we are now looking forward to, for example, introduce cellular networks. So 5G is obviously of much interest, and also LTE. But we are still collecting data from the actual factory floor in order to be able to accurately simulate this networking technology.
So you mean LTE could be a reasonable technology for this kind of architecture, also not only 5G?
For the modeling architecture, yes. And as far as I know, LTE also includes a side link capability. And in this case, LTE might also be interesting for peer-to-peer communication, yes. Okay,
thank you very much. Very interesting.
Thank you for having me.
So I don't see any more questions. Thank you very much, Christian Sauer, research engineer at SAP Eurodrive, and thank you for being at the CMM.
Thank you for having me.
Thank you. Bye-bye. So we're moving to our last speaker, last but not least, very interesting field, which is drone technology. Drone operations, digital and borderless, with an integrated drone control center. And for this topic, we have here in the studio our next guest, Matthias Gronstedt. Welcome.
Welcome. Thank you very much.
Mr. Gronstedt. Matthias Gronstedt is Managing Director at HHLA Sky. Matthias Gronstedt had a large and broad experience here, I see. He has worked in the IT and automation technology with global responsibilities for 25 years. Then he started working at HHLA Strategy Consultant for Digital Transformation. And here in this assignment, he and his team developed an integrated drone control center and an industrial drone platform for use in critical industrial infrastructures. So, his knowledge from IT and automation were instrumental in first conceptually designing and then bringing to life an industrial-grade scalable system where safety, security, and the latest high-performance technology are key. And we're looking forward to hear more about this. Thank you very much.
Thank you very much. Good afternoon, ladies and gentlemen. I'd like to show you how you can unlock the third dimension for your business processes with our integrated drone control center and our industrial drones we have developed. My name is Matthias Gronstedt, and first I'd like to show you a video.
The pioneering spirit. It paves new paths, sails uncharted waters, sees unimagined potential. It rethinks how things could be. At HHLA, the pioneering spirit is in our DNA. We improve what we have, becoming ever more efficient. With HHLA Sky, we are taking our pioneering spirits to the air and finding new ways to meet the challenges of tomorrow. raising the bar for hardware and software. We're delivering tough control systems, intuitive and simple operation, to be used by everyone around the globe. We're setting the standard for the industrial use of drones. As the first provider of a globally scalable end-to-end drone system, we have but one task: to open up a world of new opportunities. HHLA Sky. Expand your business.
Yes, HHLA Sky is actually about expand your business. So when I started our project 2.5 years ago, I had a simple task from my CEO, Matthias, make drones available for our critical infrastructure in our harbor. And then that is where we actually started. HHLA Sky is a 100% daughter of the Hamburg Harbor Logistics AG, which is, we are running the containers, the container shipment. We are having our trains. We are also in logistics with cars, and we are taking care of the real estate in the Hamburg Harbor City. So what is the connection to drones with us? Today, HHLA is already a coordination center for all kinds of ships, trains, and trucks arriving and leaving Hamburg. So the logistics of tomorrow is for us onshore, offshore, and in the air. So the idea is build a global scalable drone control center for industrial use of beyond visual line of sight flights. So what is actually the issue with that? Today, a drone is controlled by one pilot, and this in the line of sight. So that means when you control a drone, basically after 200 meters in the air, you do not see what the drone is actually doing. And this is basically not a use case or for industrial use. So in industrial business processes, we need a higher degree of automation. And consider our harbor with all his terminals. There's water in between. How should one guy with a drone go to the other terminal, jumping on the boat, or what is the solution for that? So we needed to take out the guy in the middle to basically the human factor to reduce failures and risk. So how do you get to that next level to unlock the third dimension for industrial use in critical infrastructure especially? So you need to take latest technology and try things nobody has done before. So within our drone control center and in our industrial drones, we are all combining the latest technology, which is high-speed networks, virtual reality and augmented reality, artificial intelligence, cloud computing, and all this to be put together to get at least to get things done. So how does our control center looks like? It's an integrated drone control center platform running in the cloud. So when we started designing our control center software, we had three core developments scenarios, I would say. It's mobility. Yes, it's clear, drones are flying, but mobility means bring your own device. So it needs to run on any device you can think of. That was one core. Then using industrial IoT solutions to make it a bit broader and more reliable for industrial use. And then cybersecurity. This was very important for us as Hamburg Harbor is critical infrastructure of Germany. We are working 24/7 a year. And that means we have higher requirements on safety and security as usual, let's say, factories, basically. And so we designed our system according to IEC 62443, which is the Industrial 4.0 cybersecurity standard. And we, within the drone, we have already implemented machine safety. So safety is integrated in our drones to make the whole system an end-to-end solution which can be used in industrial factories. So we have built a multi-purpose drone. You can see on the first left, the drone is carrying a box, a transport case. Then we have several sensors like videos, photos, or even multispectral cameras can be used. And so the platform is designed to not even control drones in the air to make that available. So it's also designed to control robots on the floor. So AGVs, for example, or robots which are used in hazardous areas. So this is basically the integration of our control center. As it is by design, the software platform is designed to actually give you a metrics. So you can basically run one control center on terminal A, on terminal B, or in a region of northern or southern Germany, or even in US or China, or you can create a functional corporate control center, which is maybe for corporate security. So this is a crucial point to connect your subsidiaries with a clear architecture for the future, and that makes the thing completely scalable. So with our huge operating area, it's basically 7,200 hectares, where we in this area we require processes in the third dimension. So we are using our drones to inspect our container cranes and other infrastructures. And we also have hazardous areas where we are using, or we want to use basically remote controlled robots to go into these areas with cameras to see what's going on there. So we expand our business for us, and we are observing with surveillance, with drones, our critical infrastructure, our perimeters, and we are doing intra-company logistics, which is we transport with our drones documents, spare parts, and sometimes material probes for a lab to be considered there, and technical inspections. That is a huge area for us. So we are inspecting our container cranes right now, fully automatic. And the biggest fan in our company, which is maybe a good message for all of you, is our work safety group, because we are taking out human beings out of the danger when they have to climb, for example, a 130-meter high container bridge. This makes, and also if they want to basically inspect a container farm, a tank farm, which we also have, a guy needs to go in to check if there is some leakage or whatever. So it's much easier to fly over the tank farm with a drone to see if some leakage is there, and after that you can even send the guy in with special clothes into the hazardous area. So the idea behind our control center is not only flying a drone, which took some time to develop, but it is basically the workflow. The workflow is really the trick behind the control center. So it is like an ERP system for drones, basically. So software is only a feasible standard kind of thing, or to be used when regulations and standards are included in the software. That's why, for example, SAP or Oracle's others are so successful, because you can trust they have IFRS and all these things included into their software. So our workflow in our control center is about preconditions. So you need to check all regulatory qualifications of your guys flying the drones, certified flight trainings needs to be done, and then the drone needs to be registered. Registration plate, and also identity management needs to be done by the control center. You have to check and prepare the drone and the sensor equipment before you start the drone. So we have implemented a mobile technical workplace, which does a pre-flight check and post-flight check, for example. The mission planning is included in the control center, and where you can check if no-fly zones are available, or you can set up a geofence around your flight path and transfer the flight data to the drone. and after the flight has been done, all data is downloaded into the control center. Flight execution, this starts the drone and flies the drone and monitors all telemetry data from the drone, maybe, for example, battery status, and also other safety functions are implemented. Data processing is, we have built a data archive, I will show you shortly, where all raw data is being stored, like videos, photos, and all these kinds of data. And then, which is very important, is the maintenance, repair, and overhaul. This is also included. We are building data analysis platforms, workplaces for the drones to be easier to be checked, and all this. So we have basically now 2 trump cards. Our integrated control center is managing all standard processes from registration, identity management, and flight coordination, up to billing if you want. That can be integrated into an ERP system to send out data if you want to bill the services or invoice your services you are doing. Mission control unit monitors the drone airspace and controls the drone. And we have always a direct connection to the drone, which is also encrypted for sure. So on our multi-purpose drone, it's a robust industrial drone. We have an open modular architecture, which means the drone can be used as a manual drone and can easily be upgraded with our technology to a fully automated autonomous drone in the air. We have a multiprocessor architecture for control and also for security and safety on board. Our AI processors for object recognition. We have video streaming. So this is maybe an interesting case. We have done everything programmed by ourselves in Hamburg, and including the video streaming. So what is so important about it? Video streaming is usually done with media servers in the middle. And imagine the case if there's a big fire in Hamburg Harbor and the police and the fire department wants me to observe with my drones the huge fire, and then the video stream stops. I don't think I get any minute to explain that's not my fault. And that's why we programmed everything on video streaming ourselves, including encoding and decoding, the media server in between, so that we are having actually the hands on every single bit what is running on our drone and even in our control center. So, and we are quite happy about it. So the latency of our HD video from the drone camera via the mobile network, via the cloud into the client is lower than 800 milliseconds. And this is what we think is quite an achievement. And it's, as I already said, it's permanently an encrypted data link. So the idea of the multi-purpose drone is to put many different sensors below it. For example, thermal scan or videos or LiDAR sensors, or even a transport box you can see here. The drone is having a parachute when it goes down to reduce the falling speed, and also we have a buoy. This is what we need in our harbor if the drone maybe has a mistake and falls into the water, so we can rescue the drone basically. Now I like to show you a little bit of our user interface. This is a drone control center. We have built 7 expert workplaces, which means you don't need to be an expert to run these workplaces or to use the software. The software basically supports your expert work, and this is important. So we have a mobile technical working place. We have a workshop, which is an inventory management. We have the planning software. We have a scheduling software where you can schedule drone flights and various kind of drones. We have mission control software. We have a dashboard, what you may know from TV at the NASA. And we have a media archive where all raw data from the drone will be stored. So here you see the inventory management. On one side, all drones are managed in the system, and the identity management, registration, all these kind of things are done in the drone management. Then we have reference beacons, basically, which are used for us, which we use to control the drone when it's flying around our container bridges, because the container bridge never stands at the same place as it does one day before. So there needs to be a beacon on top to do a transfer between the routes the drone has to take. And we have cameras, inventory management. That means all these kind of different lenses, data are stored into the camera inventory management to be used by other microservices in the control center. So this is how our planning user interface looks like. In the middle you can see, which is quite a general thing, you place your waypoints, and in the bottom you see a time scale where you can set video streams. The camera angle you can already see, which is the blue kind of angle thing in the middle, and this is how you can see where the camera of your payload is looking at. We can also set up object recognition. There's a little button on the left side, and this is how the planning works. You set up the geofence around the route. And we have a mission control user interface. So that means in the bottom left there is a drone which is ready to start. In the middle you can see there is a start button to be clicked, and it's running up. It's not only that you by accident click the button and the drone starts if you don't want it, or by accident has clicked it. And then you can see all drones in the air, which is on top. And you can also look into the mission in the middle of the field, and on the right hand you can see the live video stream from the payload camera and from the first person view camera. Here's the dashboard, which is very important. So it does give you the overview about your airspace. And for us in the harbor, we don't only see planes, which you can see on the left in the front overview. There's the two little red buttons are two airplanes which are at the Airbus airport, and our drones are next to it. And in the middle you can see our drones flying on our terminal Altenwerder, and on the left hand you have all these little white spots there. These are all the ships which are right now running in the harbor, and this is very important. So our overview, our dashboard integrates drones, planes, helicopters and ships to give you a full view what is going on around my drone missions. So what do we actually have? We are selling a integrated drone control center, which is used for drones and also for robots in the future, and an industrial drone. What is so unique about this drone control center? We can fly more than 100 drones in parallel, and so we have created a real end-to-end solution for industrial use of drones. What is our portfolio? Our products is the software, the integrated drone control center, which exists of the planning software, inventory management, schedule software, simulation software for drone missions, mission control, situation report view, the dashboard I already showed you, service technician, the mobile client who does the pre-flight check and the post-flight check of the drone, checking the environment, and you can also use the drone control center on your enterprise servers. This is HHLA Sky Enterprise, so you don't necessarily have to use it in the cloud. You can also put it on your enterprise server if you have higher security requirements according to data. The hardware is our industrial drones, a multi-purpose drone where you can put below all kinds of payloads. Our consulting services, so we do the use case definition, we do the process implementation into your business processes. This is where we are consulting you for industrial environments. We have system and IT implementation, software customizing, as we have programmed all ourselves. It's easy to connect to any other system you can think of. We have services, which is hotline 24/7, remote services. All drones are built and for remote service and on-site service. And yeah, we are at HHLA Sky, we are living the chance to set some standards and norms, create high qualified jobs. And with German engineering, we like to become a spearhead in the market. And we like to foster innovative business relations with leading industrial companies and trade companies. And HHLA will be your long-term partner to realize a sustainable integrated drone infrastructure. Why are we thinking we are able to? We already run system critical infrastructure. We coordinate traffic flows since years via control centers, and we operate complex control centers in our terminals already. So we know about machine-to-machine communication, and this is our end-to-end solution. And thank you very much.
Thank you very much, Matthias Grönstedt, Managing Director at HHLA Sky. It was a quite interesting and impressive presentation. And, well, we see here some questions which are coming from our visitors. The first one, do you also have communication between the drones to avoid collisions?
Yes, for sure. This is a very famous topic. Yes, we do have that. So if a drone flies and a crane or tree is in between in its pathway, the drone automatically flies around and gets back to its route. Yes, we do have that.
Very good, thank you. The second one, is it possible to run the drone on full autonomous mode, doing a predefined job from start to end?
Yes, this is what the drone actually is doing. It's I don't like to talk about autonomous. This is much more for me. So I always talk about fully automated. So yes, the drone flies without LTE. It flies its way passes. This is exactly I think the answer to the question. Yes, it does fly autonomously, but we have always a connection to the drone, an online connection to the drone. Why is that? Because with every machine in industry, we have an emergency stop, right?
Yeah.
Why do we think we don't need that for drones? Yeah, so that's why we've built it like that way.
So that means you're able at any time to get control of the drone?
Yes, we can also control the drone manually.
Okay, yeah.
Getting out of the autonomous flight into manual.
Oh, very interesting. What technology are your drones relying on? What cellular technology are your...
We are using right now LTE, which is actually an interesting thing. We found out LTE is much better in the air than on the ground, which is fascinating. But we are also able to do 5G.
Okay, thank you very much.
We have already tested that.
So thank you very much, Matthias Grönstedt, Managing Director at HHLA Sky. It was a pleasure to have you here at CMM with this topic, industrial drones.
Thank you very much. Hope you liked it. Bye-bye.
Bye, thank you. So if you're interested on this topic, industrial drones technology for industrial and use and intralogistics, the VDMA is dedicating a separated working group, Industrial Drone Solutions. So if you want further information on this topic, please visit the VDMA site, website related to the working group, ids.vdma.org. And so, ladies and gentlemen, we just finished our OEM session at the CMM. It was a pleasure to have you here. My name is Miriam Solera, and I say goodbye. Thank you very much. Auf Wiedersehen.